Good afternoon or good morning. My name is Steve Ferguson, and we're pleased to welcome you to the Washington Laboratories webinar series. We hope you'll find the next hour or so useful and informative. We've developed our webinar series to deal with some of the technical administrative issues that our customers face on a day-to-day basis. We recognize that engineering challenges can be complex, and we're always looking for ways to support the technology industry. You should be seeing our introduction slide. Welcome to the Bruce Six-Pack, Episode 1, The Ground Myth. This is the first of many parts. And in order to reach out to us, I'm going to provide some contact information. Washington Laboratories through the Academy at WLL.com, or our phone number, 301-216-1500, or you can reach Bruce Archambault directly, bruce@brucearch.com. A few housekeeping details we'd like to take care of. The attendee sound is muting for the highest quality audio. And a recording of this event is underway. We will provide the recording to all registered attendees whether they have logged in or not. Anyone that paid for the attendance gets the recording and the presentation. The chat function can be used for comments, or you can always email willie@wll.com with your mailing address, or you can reach out to any of the contacts we list here. You may want to use a full screen view for the highest quality video. That way your slides will show up in a full screen format. And again, as indicated, you can use the chat function or the Q&A functions to send your questions and comments. Don't hesitate. We will go over the comments and questions at the end of the presentation, not interrupting the presenter during the event. As I mentioned, the six-pack of Bruce has got some upcoming webinars. Here's the schedule for those, for 5 more events that are currently scheduled. Hopefully, all will sign up for the complete package or any that you see fit. The presenter, Dr. Bruce Archambault, is an IBM Distinguished Engineer Emeritus at IBM Research Triangle Park and an adjunct professor at Missouri University, Rolla, Missouri. He received his BSEE degree from University of New Hampshire in 1977 and his MSEE from Northeastern University in 1981. He received his PhD from the University of New Hampshire in 1997. His doctoral research was in the area of computational electromagnetics applied to real-world EMC problems. He held positions at Digital Equipment Corporation and Seth Corporation, supporting product design and electromagnetic analysis. In 1997, he joined IBM in Raleigh, North Carolina, where he is the lead EMC engineer responsible for EMC tool development and use on a variety of products. Bruce has authored or co-authored a number of papers in computational electromagnetics, mostly applied to real-world EMC applications. He is currently a member of the board of directors for the IEEE EMC Society. He's the author of the book PCB Design for Real-World EMI Control and the lead author of the book titled EMC Computational Modeling Handbook. He has lectured at the University of Oxford for the past 13 years. With this, I'd like to introduce Bruce, and let me allow you to do the presentation, Bruce.
Okay. Hello, everyone.
Show your screen.
Yep. Okay, and let me get into full screen mode here. Okay, Steve, is everything looking okay at your end?
Yes, everything is fine, Bruce. Welcome.
Okay, great. Thank you. And thanks for the introduction, Steve. And welcome, everyone. So today, I'm going to talk about one of my favorite soapbox topics, the ground myth. I think that the term ground is one of the most misunderstood things that electrical engineers have, unless you're working with power AC power lines and so forth, where ground really does have some meaning. For those of us that are double E's and working in electronics, then the idea of ground is something that we really need to unlearn, I think. So one of my favorite phrases is ground is a place where potatoes and carrots thrive. And this just helps to remember that our circuit boards really don't have ground on them. I think that the term earth that the British use to describe the third wire safety line in the AC power connectors is very descriptive, because if nothing else, I've got a good visual there. I understand that there's a wire connected to that plug that goes to a pipe or some building steel that goes down into the ground, the dirt, and that's fine for safety. But for us, with our circuit boards, the term reference is more appropriate. And in fact, for a little while there, some years ago, I tried really hard to stop using the word ground at all and just called it reference. But I found that as I talked to a lot of people, they weren't quite sure what I was talking about. So now I try to use the term ground reference, because everybody thinks they know what ground is, and when I add ground reference to it, then everybody's kind of reminded that it's not really the dirt that we're talking about, it's really the reference for our signals. In a few minutes, we'll talk about where I think the original use of ground came from, but the bottom line is going to be that's going to control all this is inductance. And as we go higher and higher in frequencies, the amount of inductive impedance we have goes up. And so the likelihood that the current is going to go where we think it might is diminishing, because no matter what, current will always find the path of least impedance. And we'll talk some more about that in a few minutes. When we say ground, what we really mean typically is maybe the reference for the signal, maybe the power return, DC power return, or maybe the safety earth. We have to always have our safety earth, because if there's a fault and we kill customers, that's bad for repeat business. And then the other thing that we might be calling ground is the chassis shield around our product. When you get into the EMC chamber and are doing emissions measurements, typically we have cables coming out of the chassis, and oftentimes the chassis becomes the reference by which the cables are the antennas. And so it's kind of like a lumpy dipole antenna, where in dipole antenna you have two wires with a source in between it. Here we have the chassis shields on one side and some cable on the other side to form the antenna. So the chassis shield sometimes is considered ground, if you will. So it could be any one of these things. And one thing that ground is not is a current sink. I had an engineer sit in my office some years ago now who told me that he didn't have to worry about returning current to its source, because he was just going to dump all the EMI noise into the clean ground, which in his case was the chassis that goes around the metal chassis around the product. And I said, you think this is like your kitchen sink, where you turn on the faucet and water comes down and goes down the drain into the ground and never thought of again? Actually, when you think about it, the water does get recycled in that it goes into the ground, finds its way to an underground stream and ultimately to an underground river, probably gets to some sort of a above ground river at some point, into a lake or ocean or someplace, and then gets evaporated back up into the clouds, rains back down into the reservoir, and maybe shows back up at your kitchen sink a long time later. Very big loop, very big amount of inductance, I guess, for water. But from electronics point of view, what we have to really remember is that the current must always return back to its source. That's one of the things we learned in our first double E class, is that current always returns back to its source. And once we get out into the world, we start thinking about voltage, and oftentimes we forget about what's going on with the current. So where is ground? Years ago, probably one of the smartest men I ever met, Dr. Albert Rulli, told me that ground is where there's zero potential. And so I said, okay, well, where's that? Well, zero potential happens at infinity. And so basically, if we want to measure something relative to ground, we're going to need a really, really, really long wire, right? But even if we don't go with all the way out to zero potential, let's just say we want it to be at the same potential. And so some potential, whatever it is, doesn't matter if it's zero with respect to the universe or not, just the same potential locally. Well, if we start thinking about that, if I had a steel reference plate that's 1 foot by 1 foot by half an inch thick, you can see here on these slides that at a gigahertz, I've got nearly a half an ohm across that 1 foot by 1 foot steel plate. Now, if I'm using that steel plate as my return current path, if I've got 10 milliamps of current going back to its source through that steel plate, then I've got 10 milliamps, almost a half an ohm, and I'm sure you remember Ohm's law, and you can figure out that there's a voltage drop across that steel plate. And the same sort of thing happens with our copper planes and our printed circuit boards. And so there's going to be a change in voltage across that copper plane or steel plate, and that's going to mean that we don't have a constant voltage there. We have some varying voltage there. And even if we think about, I'm going to take something as small as a via and connect the back end of a capacitor to a ground plane in the circuit board, you can see that depending on exactly how long the via is and the width and diameter and so forth, we might consider it to be about 2 nanohenries. And just using the simple formula to find what the impedance is of an inductor at 2 nanohenries at different frequencies, you can see that at a gigahertz it's 13 ohms, and 2 gigahertz is 26 ohms. And so if I've got a 50 ohm system and I think I'm connecting a capacitor to 0 ohms, well, I'm doing that through 13 or 26 ohms depending on the frequency. And so it's not really 0 ohm connection at all. And then the other thing that people remind me about is the single point ground. And at high frequencies, that's completely impossible. At low frequencies, it's very possible. But at high frequencies, we've got parasitic capacitance, parasitic inductance, and in fact, this can be called the hidden schematic because, you know, we have our schematics with all the various components and the discrete capacitors that we plan to put on the board and all that. What we don't see on there is between every one of the traces, we have some amount of mutual inductance. Between every metal trace and every other metal object, we've got some amount of parasitic capacitance. And so these parasitic inductances and capacitances are relatively small compared to many of our component values. But then as we get higher and higher in frequency, some current will go in any possible path. You know, an analogy I like to use is we're going to take a 1 volt battery and put a 1 ohm resistor across that 1 volt battery. And if we remember Ohm's law, we know that there'll be 1 amp of current going through that 1 ohm resistor, right? But now if I take and put a 100 ohm resistor in parallel with that 1 ohm resistor, so I've got 2 resistors in parallel, I know that some amount of current will be in the in both resistors. Excuse me a moment. Excuse me, I've got a cold and I'm trying to go on mute when I'm about to lose control and cough. Okay, so we know that there will be some amount of current that goes through each of the resistors. And if we remember our basic EE, we can calculate what that is. We don't have to do it in our heads. It's relatively simple algebra. But the point is that all possible paths are going to be used. And if I put now a 1 megohm resistor in parallel with the 1 ohm and the 100 ohm resistors, again, the current will sort itself out to find the overall path of least resistance and put an appropriate amount of current in each one of those resistors. Certainly, the 1 ohm resistor gets still the lion's share of the current, but there's still going to be some current in the 100 ohm resistor and 1 megohm resistor. And that's really what happens with these parasitic inductances and capacitances. There are other paths, and at higher frequencies, they become more and more attractive because potentially some of the intentional paths have much higher impedance. And so the idea of single point grounding was that we would have the same amount of resistance and inductance between our local printed circuit board reference planes, ground planes, and some single point ground, maybe the metal enclosure in this example. But what you don't see here is all those parasitics that I was talking about. And basically between all possible pieces of metal, I'm showing parasitic capacitances. And while I don't show them, there's also parasitic mutual inductances. And so all these possible paths make this idea of single point ground impossible at high frequencies. So where did the idea of ground originate? Well, I've come up with a couple of thoughts on that, and maybe the teletype connectors or lightning protection is where the idea came from at first. So we've all seen cowboy movies, and there's usually a bad guy who decides he wants to rob a bank, and so he's going to cut the telegraph wire between two towns so that people from the other town can't come and help. Now, I never really understood this because the towns are like 30 or 50 miles apart, and all they had was a horse. So how fast could help get there? You know, just don't hang around, buddy, you know. Get on your horse and get out of there once you rob the bank. But Hollywood didn't ask me, so now if Clint Eastwood was the bad guy, he's going to shoot the wire. Arnie Schwarzenegger would blow up a couple telephone poles, and everybody else climbs the telephone pole to cut the wire. But wait a minute. We know that current is going to go out on the telegraph. It has to return somehow. Originally, they had two wires, but they quickly discovered that if either of the wire breaks, the system is down. And, of course, two wires cost more than one wire. And so very quickly they found out that if they were to just connect the second wire, the second terminals into the dirt, into the ground, then the return current could happen in the ground. Now, of course, you think about how fast was a teletype guy able to communicate, you know, a few bits per second, right? Now we're at hundreds of megabits per second, gigabits per second, tens of gigabits per second. The loop area associated with the wire at the top of the telephone pole and the ground, spanning maybe 30 miles to the next town, would be a tremendous amount of inductance by our standards today. But back when we only were doing this thing with 5 bits per second or 10 bits per second, whatever it was, that was an acceptable thing. The other thing is, out in the American Midwest, you know, it's very flat. We get some very severe storms and often associated thunderstorms and lightning. If lightning strikes a building, lightning tends to be attracted to the tallest structure. If lightning strikes a building, the building burns down. That's a bad thing. But they discovered that if they were to put this large metal pole on the building and connect a wire down to the dirt, down to the ground, then when lightning would strike, the electricity would go through this wire into the dirt and the building would be saved. So clearly grounding is good. In fact, you've heard of the Human Genome Project and tried to map up all the different genes. They actually have discovered that one of the genes makes us think that ground is good. And so I point to it here, and I hope you realize I'm kidding. But I think it must be in our genetic makeup to think that grounding is good, because the number of times I've heard someone just say, do a better ground, or ground it better, or add more ground is tremendous, and that's not always a solution. So again, when we say ground, we often are talking about signal reference, probably most often talking about signal reference, but it might be the power, DC power return. It might be the safety earth or the chassis shield, and we'll have these different symbols often on our schematic. And I came across some other schematic symbols here some time ago, and I encourage you to use these. You know, I'm a sailor, so I really like floating ground. There's earth ground down there, and there's grounds for the horse, which is always interesting. And there's a number of others that you could use, and I encourage people to use these schematic symbols on their schematics because if nothing else, it'll help you make sure you understand that you're not taking the term ground seriously. Of course, I'm not sure your manager would be amused about it as we might be, but anyway, it's something to consider. Now, as I mentioned earlier, the current will always follow the path of least impedance. At low frequencies, this means the path of least resistance. So in the example I gave before of the resistors in parallel, the current sorts itself out, basically, so that it will go in the appropriate amount of current into each resistor, so that overall the resistance that is shown to the battery is the lowest. But at high frequencies, it's going to be the lowest inductance. And what oftentimes people don't realize is that the changeover happens at about 100 kilohertz typically. So here's an example on a system level. I've got a large ground braid. Everybody knows that large ground braids are good things, right? And low inductance and all that kind of thing. And then I've got a data cable that has a ground wire in it. And I'm going to send a signal through that data cable. And the return current at low frequencies is going to follow the path of least resistance, which means that large ground braid is going to be the return current path. At high frequencies, that loop area is a very large loop. And so the current is not going to tend to go that way because the path of least inductance is going to dominate. So now I've got my signal current, and now the return current is not going to use that braid at all. It's going to use the ground wire that was in the signal cable, even though it's a much longer path, probably a much higher resistance path than the ground braid was, but it's a much lower inductance path. Okay. And so when we start thinking about terms like ground loops and things like that, what I always say is that if you've got a ground loop, the question I want to ask is, why is there current going that way? How did you not just, give a good enough current path so that you wanted the current to use so that it's finding some other path? Now, when we have a schematic, we'll have ICs. Oftentimes they're just block diagrams. Here I've got a little bit more pictorial. But you can see that current comes out of IC1 on a trace and goes into IC2 and then returns through ground back to its source. So other current comes out of IC2 and goes into IC3 and returns back to its source through this wonderful, magical, mystical ground symbol that we have here that assumes there's absolutely no distance or no impedance between them. But in real life, what we have is a more three-dimensional setup. And as current comes out and flows in a trace, it's got to get back over some distance back to its driving IC. And so the path that current takes is going to be what dominates. In fact, quite honestly, in my training seminars, I very clearly say that the number one thing and the number two thing about EMC problems on printed circuit boards has to do with the return current path. If we only just design a return current path properly, then we can eliminate about 90% of all the EMC issues with printed circuit boards. So just to kind of illustrate a little bit more, here I've got a trace with currents on it with the yellow arrows that are shown, and you can see that at low frequencies, the path of least resistance is a straight shot from the receiver to the driver through the ground reference. But of course, that's a fairly large inductive loop, and we know that inductance is proportional to the loop area, so the larger the loop area, the larger the amount of inductance we're going to have. Once we get up to high frequencies, now the return current is trying to follow the path of least inductance, which means the smallest loop area. And so now the current's going to take a longer path, but follow right underneath the trace. And, the trace is only maybe 10 mils above the ground plane, or some small number like that. And so even though one of those traces might be 4 inches, another one might be 3 inches, that loop area associated with 7 inches of trace times 10 mils is much, much smaller than the low frequency case where I had 3 inches, 4 inches, and a 5-inch diagonal, and take that loop area is much larger. And so the inductance is much larger in this example where we're taking the path of least resistance, and the inductance is significantly lower when we take this longer path, even though it's longer. Now, to kind of illustrate this for you, I took some simulation tools, and I've got a case here with a printed circuit board, and you can see some of the dimensions there. I've got a simple source at one end of the trace over the ground plane, and where the load is, actually, I'm just going to short that out to the ground plane. So I'm going to drive some current onto the trace. It's going to go down from the left to the right, then from the top to the bottom, and then from the right to the left to where the load is marked. And then the question becomes, how does the current get back to the source? Again, I'm just shorting that trace to the ground plane. I could have put a 50 ohm load on there or something. It doesn't really matter. At low frequencies, I'm going to expect the current to take that short path directly from the part that I had labeled load to the part that I had labeled source and through the ground plane. But you can see that that's a very big loop area. So this works at low frequencies, but not at high frequencies. Now, at low frequencies here, let's say 1 kilohertz, you can see this, we're looking at the current density, and you can kind of see in the along the left of the circuit board ground there, the yellows and the reds of the current density showing a very high current density for the return current in that ground plane. However, if I go up to 1 megahertz, you see that in that ground plane between the source and the load, there is no currents there. All the currents actually are going back underneath the trace back to its source. Even though it's a much, much longer path, it's a much lower inductance path. So, how does the inductance actually get to change? And it's because the current path changes. So here I've got a different simulation tool where I mentioned I grounded the load. I just shorted the load to the ground plane in my circuit board from before. And now I measure the inductance that the source sees as a function of frequency. So you can see at low frequencies, I'm getting quite a bit of inductance, more than half a microhenry of inductance. And at very high frequencies, you can see that my inductance is much lower, less than 0.3 microhenries. And there's a transition region where I'm going from high inductance to low inductance. And again, the only way that inductance can actually change is by actually changing the path of how the current flows, rather. And you'll notice that the changeover starts at about 10 kilohertz and is completed by about 1 megahertz. So what this means is that by the time we get up to 1 megahertz, we really should be thinking about inductance as a dominant factor in our current flow and not resistance. Okay? And I think most of us are working in areas where 1 megahertz is not the highest frequency that we're dealing with. We're probably working in tens of megahertz, hundreds of megahertz, and even gigahertz and tens of gigahertz nowadays. So the return current is very different than what that simple model that we start out with was. Now, I like to include this slide. A friend of mine years ago told me there was no such thing as voltage. Well, this was a real shock to me because I had a voltmeter. But what he meant was if we look at Maxwell's equations, and we're not going to do that during this session, but if we look at Maxwell's equations, we're going to find out that Maxwell's equations describe electric fields, magnetic fields, and current. The voltage is actually a man-made structure or construct of the electric field over some distance. And so we measure the voltage along some path. It might be between two terminals that are right next to each other, or it might be between two terminals that are further apart. As long as the distance between them is very small compared to the wavelength at the frequencies we're working with, this formula works just fine. And but again, it's not a fundamental quantity in the universe. Electric fields, magnetic fields, and currents are a fundamental quantity in the universe. And so when we think about EMC and proper EMC design, we really need to think about where's current flow and how do we control the current flow. And then as far as what radiates for emissions point of view, we can also look at this simple formula. Well, it's not so simple, I suppose. But really, when you look at it, inside the parentheses, we've got omega. That's frequency. So we're going to work one frequency at a time. C is the speed of light, so that's not changing. R is the distance from our observation point to that current, so that's not changing. So everything inside the parentheses is a constant. And then actually, outside the parentheses, sine of theta is just the relative angle between the current and the electric field, so we'll make that 1 for maximum. And 4 pi epsilon is a constant. And so really, all that stuff is a constant, and the only thing that the electric field is proportional to is the length of the electric field wire and the amount of current we have on it. And so again, current is what we worry about for radiation, not for voltage. So, when we start thinking about current flow in our electric fields class, they often will use an analogy of a hose with a marble in it or something. And so we've got this wire that electrons are flowing down, similar to having a hose with marbles in it or something, and they must return back to its source. And as long as the current is flowing, my little electron is going round and round here. as long as the current is flowing, the light bulb is on, and everything is fine. If we break that path, then the electron can't flow, and the light bulb goes off. Okay. Now that's a very simple thing. It's a little bit more complicated than that in real life. Now they also at school will then talk to us about alternating current, where current will flow in one direction during one half cycle and flow in the other direction during the other half cycle. But again, this is low frequency thinking, fine for 60 hertz power in the wall, 50 hertz power if you're in Europe or Asia, but it's not what we're dealing with on our printed circuit boards. Really what we have on our printed circuit boards is a pulse of current. And so current must always return back to its source. Now, it's not going to be that the current goes for a trace, from a source on a trace, all the way down the trace to some load and then comes all the way back, similar to that light bulb picture I was showing before, unless that path is electrically short. If the path is electrically short, meaning short compared to a wavelength, then that's not a bad analogy. But as soon as that path starts to get long compared to a wavelength, and by that I'm talking about maybe on the order of between a 10th and a 20th of a wavelength, then we have a pulse of current. Excuse me. Oh, I'm back. I apologize. All of a sudden, I lost control again here, my cough. So the current is going to exist only a short pulse. And so it's similar to tank treads. You can think about the current underneath the trace as being the upper tank tread traveling in the forward direction. And then in the reference plane right below the microstrip or strip line, traveling back. And at the ends, it'll be going around like the tank treads do, through displacement current. But the bottom line is that the current is still in a loop. So here's a simulation that kind of shows that. And what we're looking at is current density in the ground plane. And you can see that it's only existing in that short pulse area there. I'll go back and do it again. Here it comes. So you can see that the current is only existing over a short pulse. And so the current is not, again, going all the way down the trace, on the trace, and then through the load and traveling back on the ground plane. We have this pulse of current coming down. This might be a little bit easier to see. Here I've got a trace. We're looking at a side view of a trace, a side view of the ground reference plane. And the current pulse and the voltage pulse are traveling from the left to the right. As soon as I start up the animation anyway, they will be. And so I've got current on the bottom of the trace that's traveling from left to right, but it doesn't go all the way down to the load. It uses displacement current capacitive displacement current to get down to the ground plane, and so that we see the return current or the image current in the ground plane, and then we get at the back end we get the current going back up. Actually, those arrows on the back side are in the wrong direction. I apologize for that. But you get the idea that we have this pulse of a loop of current that's traveling down the trace. So it's a lot different than what the marble and the hose kind of analogy that we learned in school. Now, when we start thinking about some more realistic structures that we might actually have in our circuit boards, we could have microstrip transmission lines where we have a transmission line on the outside of the circuit board, on the top and the bottom, and some kind of a ground reference plane below it. We might have a symmetrical strip line where we have solid planes above and below the transmission line itself. Or we can have almost any kind of structure that we might want. Oftentimes we might decide that because of cost constraints that we can't have our signal lines have dedicated return planes to them, ground return planes to them. So we might have to put a couple signal lines in between a pair of planes. And in fact, in this case here, maybe that maybe we're going to send our signal down on the top layer there, the microstrip way at the top. But maybe that next layer down is 3.3 volts, and then the fifth layer down there, the next solid plane is 2.7 volts, and then the next one down is 1.8 volts, and ground is the one that's way near the bottom there. Our schematics tell us that all the return current is going to be on the ground. But we can kind of think about this in a 3D view. If we were to kind of rotate this a little bit, we can see that the loop area associated with returning the current on that bottom ground plane is much, much greater than if the current was just to stay on the nearest plane, regardless of what we called it. In fact, quite honestly, we can call these things, these planes, Detroit, apples, and and whatever we want. It doesn't matter because the electrons don't go read the schematics and see where they're supposed to go. They just go where physics and Maxwell and God tells them to go. So this next series of charts shows the electric field lines. The blue lines there are the electric field lines. And wherever they terminate on metal, that's where there's going to be current. The circular lines are equal potential lines. They're not magnetic field lines. But you can see that most of the current density, most of the density of the electric field lines is directly underneath the trace, and they terminate on that VCC line. The ground plane is actually a couple layers below that VCC line that's on there, but they don't go through the electric field lines don't go through the VCC plane. They just terminate there, and so there'll be return currents on that VCC plane. You also notice that there's a few electric field lines that go out at an angle and terminate further out. And so while most of the return current is directly underneath the trace, some of the return current will actually spread out trying to find the path of least inductance. It turns out that the path of least inductance is certainly associated with a path of least loop area, but also it has to do with low current density. And so that's a subject for one of the future seminars, but that's why the current actually spreads out. So there's a balancing act here between keeping the loop area small and the current density as minimal as possible. And while the loop area is the number one factor, the current density is still a factor to be considered, and so we get some of the electric field lines and some of the return current that actually spreads out. Now, if we look at the common mode, where we're driving both of these traces with the same exact signal, it's not that much different than the previous chart, but we had the field lines in the middle that used to go out to the far reaches now see an equal and same charge, and so they repel each other and go down to the ground plane, the ground reference plane, or VCC in this case. However, the differential mode is a little bit more interesting to see. You can see here that now I'm not driving the signal line relative to any kind of ground reference or anything. I'm driving it signal line 1 relative to signal line 2. And so we would think that that was differential and there'd be no currents on the ground plane. Well, you can see that there is some coupling between the two traces, those blue lines that go directly from one trace to another. But you can also see there's more of those blue lines that go directly from the trace down to the reference plane. And in fact, these are more closely coupled to the reference plane than they are to each other. And if you were to take some signal integrity tool that's either your company has or that's free on the web, and take two traces that are side by side, similar to what I've done here, and change the distance between them by a factor of 2, you'll see the differential impedance will change by a bit. put them back where they are, and then change the height above the reference plane by a factor of 2, and you'll see that the differential impedance would change a lot more by that height change than by the separation change. It's because most differential lines are what we call weakly coupled and together, but they're very strongly coupled to the nearest reference plane. So there will be currents on that reference plane. If we go into a strip line, a symmetrical strip line, here I've labeled one metal plane as ground, one metal plane as VCC, and you can see that the electric field lines don't care. The same amount of electric field lines are going to both, and therefore the amount of return current that's on those two planes is going to be the same, regardless of what we call them in a schematic. And if I go with differential, again, I have some coupling directly between the two traces, but most of the coupling is to the reference planes. And again, it doesn't matter whether they're called ground, VCC, Detroit, or apples, it doesn't matter. And then if I have asymmetrical strip lines, where I'm coming down about a third from the top, and there might be another trace running perpendicular to this one, another third down that's not shown here, you can see that most of the field lines couple to the nearest trace, whether it's called ground or VCC, it doesn't matter, it's the nearest trace, and there are some coupling to the further trace. And if we go with the typical 1/3, 2/3 for the signal lines, then 2/3 of the return current for this example would be on the VCC plane, and 1/3 of the return current would be on the so-called ground plane. And finally, the differential case for asymmetrical strip lines, same thing as before. You can see that some of the coupling goes between the two traces, but the strongest coupling is to the nearest plane, and still significant coupling to the further plane. So just to kind of summarize all this, the idea of ground is very misleading. I think that the number one thing and the number two thing that causes EMC issues on printed circuit boards is all about return current and this idea of ground. And if we just make sure that the return current flows well where we intend it to, then we're going to reduce those problems on our printed circuit boards. The key really is, where does return current flow? And so remember that for low frequency, we can think about resistance and minimal resistance path. But for high frequency, and that for us now, I'm defining that as everything over megahertz, we need to minimize the inductance. The current will always get back to its source. It has to get back to its source. It will, no matter what you do, get back to its source. Otherwise, it couldn't function. Now, the only question is, do you feel lucky today? Because the path it takes may be fortuitous for you, but it may be not fortuitous, causing lots of emissions and other even signal integrity problems. And always remember, Bruce says, ground is a place for potatoes and carrots. So that's the end of the presentation. Thank you very much, and I'll be more than happy to answer questions.
Thanks, Bruce. That was good. I got an inquiry on slide 19 where you indicated a changeover at 100 kilohertz. What parameters can affect that frequency?
Okay, so the parameters that would affect that frequency would be the physical size. So if I had something that was relatively small, then that frequency might be much higher. You can see, though, from the dimensions in my example here, I had 22 inches of trace total from one end to the other. So the total circuit board was only something like, I think the trace was about 8 inches and 4 inches and 8 inches back, or something like that. So this is not a very big circuit board. And from this example, the changeover was all done by the time we got to 1 megahertz when we looked at this curve here. You see that 100 kilohertz is right in the middle of the changeover. So it depends on the physical size, but somewhere in the kilohertz to very low megahertz region is where the transition is going to be for most things that are being done today.
So what you're saying is a smaller area would shift this curve either left or right, depending on the shape and function.
Right. A smaller area would shift this curve to the right, so that the frequency where you worry more about inductance would be higher because the loop area is smaller, so that means the amount of inductance is smaller.
Okay, good. I got an inquiry could you review number 42, just about differential? Just pass through again.
Sure. So in this case here, I'm driving one trace relative to the other trace. And so my voltage driver from my IC didn't even have to be connected to ground. But what we're seeing here is that while I have some coupling field lines, the blue lines there directly from one trace to the other, that's the coupling directly from one trace to the other. There's more field lines that go down to the VCC or the reference plane. And so that means that there's going to be more coupling between these so-called differential traces and the reference plane. And they will have a significant amount of return current on the reference plane. And then any discontinuity in that reference plane can start to cause EMC issues. I know that when differential signaling first came out, it was considered to be a big good thing for EMC because now there wouldn't be any return currents on the ground planes, and we wouldn't have all these problems, and they could have breaks in the ground planes or whatever, and it wouldn't affect it. But that's not true. It turns out that the amount of current that we have on the ground plane is significant. And then the other thing that I really didn't get into here is in one of the future seminars is that a little bit of asymmetry in the transmission lines here will cause what's called skew, and that delay from line to line delay causes common mode noise, which means that instead of having one of these traces blue and one of these traces red, they're both red. So I have the same signals going down on both of them because of this skew, or it might be Rice-Fault time mismatch, or it might be because one trace gets too close to the edge of the nearest ground reference plane. There's a long list of things that can cause this. And then any discontinuities in that ground reference causes serious EMC problems.
Would the positioning on adjacent layers versus adjacent on the same layer have an impact on this differential coupling?
Yes, it would. If I had the traces of one above the other rather than side by side, then I would have a lot more coupling trace to trace and less coupling to the nearest reference plane. However, that's actually difficult to do in practice because as you route those signals, you're not allowing any, if you're routing these two signals north-south on your circuit board, you're not allowing any east-west routing on that layer, in that area. So it turns out to be fairly hard to do. I have seen it done, and it's actually from a EMI point of view a better thing, but as all things with trade-offs in engineering, it's a difficult thing to do. But even doing that, it's not going to remove the amount of coupling. It's not going to stop some amount of coupling to the nearest ground planes. There's always going to be some coupling to the ground planes.
Okay. Those are the questions I've received at this point. Thank you very much for going over those. I've got a couple of small items. I'm going to take the presentation, Bruce.
Okay.
And again, we welcome your questions. Please contact us. And I want to look at some upcoming training. This year, 2015, the Academy has went into a multi-pack series for various topics, including this Bruce 6-pack, where 6 pieces of information or webinars are taught as a package. They can be acquired individually or through a multi-pack arrangement, including 12 packs, 24 packs, and a subscription item where you can attend any webinar offered during the calendar year for one price. So you might want to look at your training programs and see if things interest you. And by the way, buying 6 of webinars didn't have to be the 6-pack of Bruce. It could be 3 of his and 3 of something else. It can be any mix and match that you want to do that. So you can do the multi-part package or mix and match webinars as you see fit. Our website, the link in the upper corner there, gives you some details. Just hit our webpage, WLL.com, and go to the Academy training, and you'll see a list of upcoming events as we keep adding more and more topics. Again, I want to thank you very much, Bruce, for this presentation. And we will be looking forward to the next one. And I'm going to back up and get the dates for yours. I think it's February 25th is the next. Yes, it is. February 25th, we'll be going over Electromagnetics for the working engineer. We look forward to this. And is there anything else, Louis, that you have?
Nope, nothing more from me. Thank you.
Well, thanks for attending, and unless there's anything else that comes in, and I just checked, there's no additional, I'm going to end this event. Please see fit to join us for multiple issues, and don't hesitate to contact academy@WLL.com or Bruce@brucearch.com.
Okay, thanks very much.
Thank you.